Okay, good morning, everyone. So, today's what, Wednesday? So Monday we finished up in very quick fashion the small module on fluid systems and how those, even though we have different components, they look essentially like the electrical systems we looked at already. They have some common elements to the magnetic systems, and also it ties into all the work you've done thus far in your previous classes on mechanical systems and systems that are basically built out of mass spring dampers. So each of these systems have some sort of element that is common amongst them that we can look at. So all that material was fine. It's okay. This is the best thing you'll ever see. So your life will be forever changed after today. So this is controls. This is now we're starting to integrate everything together, and now we're starting to look at how this can be integrated with microcontrollers, computers, etc. So multiple systems, all combined together to perform some sort of desired task, right? And so after I took this class, when I went to Ohio State, this was in quarter systems, so we had an entire class, 10-week class only on control systems, and that's what convinced me to go to controls. I don't know if it'll be the same for you, because my professor was better than I am when I had that class, so maybe it won't be as impactful for you. But this is what I consider to be my favorite part of all mechanical engineering. I hope you feel the same. So we're going to start with control systems. We're going to talk about the general architecture, and then we'll get into some properties and why this can be so impactful. So what I'm showing here on the right plane here is the general control system. And I'm making a note here because when I learned this stuff, this wasn't always true, but pretty much all modern control systems right now, fast forward 14 years from when I took this class, have some sort of microcontroller or computer connected to the system to actually do this control. When I took this class, we had a lab here at Ohio State, and I can talk about this later, but we actually, all the logic in that lab to the controller was all done by pneumatic circuits. And it's crazy to think that still existed 14 years ago, but and they still exist actually in a lot of industrial systems as well. But most everything today in terms of modern control systems that you would actually design, I'm not saying if you work for some sort of engineering company that has really old hardware and you have to fix it, this wouldn't be the case, but if you're going to build something from the ground up, it's going to be have this divide, and we'll fill in the spots in between here in a second, but we're going to have a divide in our systems where one half of it is going to be virtual. That means it's living inside of a computer. This dotted line here is the divide, and then the other half is going to be physical. And so the physical part, this is essentially what we've been learning thus far. So mechanical systems, motor systems, whether or not that be what looks like a DC motor or voice coil motors, that'd be moving coil systems or moving iron systems. This would be something physical. And so we have this divide, and we can talk between the two of them to achieve some sort of desired task. And so we're going to, in this first part, we're just going to talk about the most important elements of a common control system. The first being what's called the reference. So the reference given by the Laplace transform of the reference signal. So if we have R of S, this equals the Laplace transform of some sort of time domain signal R of t, and we call this the reference signal. And this is your desired output. Okay, so we'll go through some examples of this in a second, but kind of briefly, this is what you want the output of the system to be. So if this is cruise control in your car, and you set it 65 miles per hour, the reference is 65 miles per hour. If it's the temperature control system in this room and everyone thinks that 73 degrees Fahrenheit is comfortable, then the reference is 73 degrees, right? And if it's a robot problem, which you'll see in the project part 3, it's going to be the position in time of your robot arm. Right. So the reference in a modern control system lives in a computer, right? This is the virtual side. And so you would, in a computer environment, specify what you want the desired, what the desired position of, say, a robotic system is at all time going forward to complete some sort of task, right? Or if this is your cruise control, this is stored in your car, right? You push the button that says set your cruise control, and it's in the engine control unit or the computer in your car, and this is specified inside the computer. Right. We have, let's do all the signals first. So now we have our output of our system. This is C of S. It's over here. So we have an actual physical output to our system. That's defined in time. Then we can take a Laplace transform of it to look at this block diagram. But this is our output signal. Okay. So if the reference is our desired output, that's more of a notion of where we want to be. The actual output is where we currently are. Okay. So in the case of cruise control, if your speedometer says you're going 63 miles per hour, then you're going 63 miles per hour, which is not 65. Right? And so this is a metric of where we currently are at, so we can compare it to where we want to be to understand how much do we have to change the input to the system. Okay. So as the output, we have another signal which was called the input. Which is right here. Which is the input signal. And so this is how we drive our system. So take, for instance, the motor system and the motor and pendulum system you're looking at project part 2. The input in that case is the voltage across the motor terminal, right? That's what drives the system. In cruise control, you could think of this as basically the accelerator angle. So whatever the angle is of the accelerator in your car, that would be your input to your system in terms of speed. Okay, so I think all of these signals, I hope, make some sense to you. The one that we're going to introduce now, we'll use often, but it's not as obvious. And so this signal is called the error signal. And it's right here. Okay, so the error signal. So the error signal, if we have our desired output, say cruise control, the desired output is 65 miles per hour, and you have a measurement of your current output, say at a certain point in time you're going 63 miles per hour, the error is the reference minus the actual, which is then 2 miles per hour. Right? Okay, so the error is a metric of how well you're doing. So oftentimes in control systems, we are attempting to drive the error to 0. Right? Because we want the actual output to match the desired output. Okay, does that make sense to everyone? Is there any questions on that basic idea? That's, I guess, one of the most fundamental things about a feedback control system, or what's oftentimes called negative feedback, and it's called negative feedback because you are doing subtraction, right? So we say that the error signal after the transducer. Which transducer are you talking about? Transducer. Yeah. So that would be the sensed output. We're not going to, we'll get into why we're not going to consider that too much in this class in a second in terms of the discrepancy between the output and the sensed output. But there is a difference because every measurement system has an artifact associated with it, which I hope you're learning in your measurements class. Any other questions on that idea? Okay. So other elements in verbiage that will be used in this class is the plant. So the plant, so this is just a word for, this is just the controls language speak for the physical system we're trying to control. Okay, so the word plant, basically, if it's the system you're looking at in project part 2, that is the motor pendulum assembly with gearbox, right? That's the physical system we're trying to control. If it's cruise control, your plant is your car, right? It's a transfer function relationship between your accelerate angle and the speed of your car. And I'll get through other examples of different plants in a second, but it's basically whatever we're trying to control. It's a physical system, right? So even though in the project you're working just with simulation, it may not feel physical, but you could buy all those pieces of hardware and assemble them together, and that's actually what you're trying to control, right? Is a physical system. All right, G1 of S. This is called the controller. Okay, so this is looking at the transfer function of the controller. So this is your main task. So we're looking at control systems here. Let's assume that we're all going to be controls engineers. I hope you are. But this is what you are trying to design. So from kind of a really high level, changing your plant is very, very expensive. Okay, so say you were to buy all the hardware for the project part 2, that's going to cost you a few $1,000s, right? Which is not incredibly expensive as far as the company is concerned. But when we're talking about G1 of S, this lives inside of a computer most days now. Changing your controller design is just changing a few lines in code, which is very inexpensive, right? As opposed to changing the plant, which means buying either a completely new system or buying new components of that system. Okay, so our goal as a controls engineer is to design a controller such that this whole system operates in a favorable manner. We'll talk a lot about what we mean by favorable throughout the rest of this class, but that's basically your design task, is to make sure that this element here works well with the rest of the system such that it achieves its goal. Okay. All right, so that's inexpensive. You just change lines in code. Then the last element here, ran myself out of space, but this is our sensor. So H of S. And so for this class, we are going to assume that we always have some sort of a sensor that can measure whatever the output is, right? So if you have an output of interest, say it's speed on your car, you need to have a sensor that can measure speed, right? So any car you buy has a speedometer on it, right? We have the ability to sense that. And in this class, we're not going to get into too many details of the sensor because that's more of a measurements principle. but we are going to assume that most sensors are quite good. And this is fairly true. This is pretty much true for a lot of systems anymore. And so when we say quite good, what we mean here is that if we have an actual output, where's my cursor? Right, this is our actual output. This is the actual speed of, say, of your car. We have a sensor that can sense that and then relay that to our computer-controlled system with really high fidelity, so that there's not much signal distortion. So by that, we mean that this transfer function is equal to 1. All right, so this is going to be our common assumption in this class. Okay. Any questions on this general idea of control before we get into a few examples that you may be able to see in the world around you? Yes?
Like, if you had some kind of system that required a bunch of, like, if, else, like, if then else kind of like logic.
Yes.
Would that look way different from this?
So the if-else would all live in G1 in a computer. Right? Assuming that you're talking about like computer logic, right? So it would look the same if those are, if all these if-else's are like if do this, if this, do this control action. It would look the same as this as long as you're working on the error signal. So here we're assuming that all your if-else conditions would be on the signal E of S. Right. If they're on something else, then it wouldn't look like this. But what you're talking about is logic statements, which usually are nonlinear relationships. Like if this is a greater than this value, do something, which you have then this really distinct transition between when you're not satisfying the if statement and when you are satisfying this if statement. And that gets much more difficult to model. That's actually beyond what we talk about in this class. We're looking at continuous time systems or continuous systems in this class. But the architecture would be the same if I understand you correctly. Carson.
Does this look the same no matter how many references and how many outputs there are?
This is like so this is what we're talking about, the standard single input, single output system, or what's called CISO. So the question is about MIMO control. This in the general block diagram looks the same, but then instead of this reference being just a single input and the output being the reference being a single desired output, the output being a single output, we would have multi-channel information. We're not going to get into multiple input, multiple output control in this class. That's more of a graduate level topic. Okay. All right, so some examples that in your everyday life where you may see this. So this is something that we talked about when we first introduced the class, is the basic idea how cruise control works. And so in cruise control, is that zoomed in enough? Probably not. Zoom in a little more. Okay, so cruise control, you have the basic idea that you would set a speed. This is done not by like programming this a priori into a computer, but you push the little set speed button, right? This sets your set speed of your desired speed of your car. And then you have an actual car speed, which is whatever you're going at right now, right? So you may notice that if you're going along flat ground and all of a sudden you go hit a hill, you transiently down a little bit. And so this value of speed is below the set point. So if this is R in the domain, R of t, this is 65 miles per hour. And this is your actual speed because you got knocked off your set point by hitting a hill. This would be then, this distance here would be E of t, right? This is our distance between desired speed and actual speed. And we'll get into this actual action of what happens, but your system is going to react. So your controller is going to be programmed appropriately so that your engine control unit changes the angle of your gas pedal element to give it more gas. So you could do this automatically if you were watching your speedometer. You can adjust the speed of your car by adjusting the angle of your foot, right? But a cruise control does this in an automatic fashion. So it would see if this is proportional control. We'll get into proportional integral derivative control later, but it would say that, okay, let's make the change in angle of my accelerator proportional to the air. So if the air is really large, I want to make the input really large to counteract that large air, and as the air gets smaller, then we can decrease this input to our system because we've reached our goal, right? Is the general idea behind cruise control. It's obviously much more complex than that, but that's the general way in which a cruise controller works in your car, and this is, what I'm explaining here is the simplest control, which is proportional control, which we'll talk about a lot. Any cruise control in your car is much more complicated than proportional control. This is like the simplest example we can get to start out. Okay, so some examples of other controlled systems. This is what is credited as being the first ever control system. Okay, so what's going on here? So the idea here, behind this water clock is we wanted to have a constant flow rate of water coming out here, so that when someone wants to know what time of day it is, they can look at where is this float relative to different marks along here. This is, when I say this is old, I forget the date on this. This is when the Greeks were still doing good stuff. So anyhow, this is the idea that you would start the day with this water completely down, and then as you go up, and you want to have this linear scale, such that to do that, you need to have the water flowing at a constant rate. Right? So it just then raises throughout the day, so you have a big clock. And so the way in which this works, it's completely mechanical, of course, no controllers back in ancient Greece. But what you had is you had this float, and this float had this kind of taper that went into this orifice, and this creates a valve. And so if you want to get constant flow rate, you want to have a constant pressure head here. So you can have a tank of water, and what this float does is that the water level gets too high, that plugs this orifice, and so you get no flow rate. And if it gets too low, then water can flow out. And so that's a way in which you can keep constant head height. So the output of the system would be essentially the height of this water column, and then it has, via clever mechanical design, the control, which that controls the flow rate of water into this first area. This is credited as being the very first feedback control system. It has feedback because they developed a mechanical system that looks at essentially the difference between the desired height, which is set as a level, and the actual height, and then changes the input in accordance to it. So very clever, simple system from way, way back that's seen as the first feedback control system. Other examples that are feedback control systems. So this is what's called the Watts governor. This is considered to be one of the first modern control systems. And so what's going on here, it's not showing the entire steam engine, but this is designed to control a steam engine. Right? So if you want a steam engine to not go too fast or too slowly, you have mechanisms like this. And so what you have here, the input of the system is basically the flow rate of air into the combustion system, which has coal in it. So more air burns hotter, more steam, right? Less air doesn't burn as much, less steam. So you can control the flow rate of air by this valve here. And so the way in which this valve is controlled is via mechanical linkages. These mechanical linkages connected to the flywheel of the steam engine. So it's actually actually spinning, which determines how fast your steam engine is going, is mechanically connected to this flywheel, and this flywheel rotates on this axis. Right. So if this flywheel spins faster, these centrifugal forces, these balls that are basically the masses here, these splay out, and what that does is it actually, via this mechanical linkage, is it closes out. If then it closes the valve, and via the lack of centrifugal force, the balls come back in, that opens the valve again. Right? So it has this natural mechanical feedback to it, such that you can control speed of the steam engine via purely mechanical methods. Right? So the output here is the speed of the engine, and then the input is this angle, and then you have this mechanical feedback system, which is always looking at, all right, what is the actual speed of the engine based on how far these balls of the centrifugal governor are splayed out, and then that can change the input. Right? That's the feedback. This was all built, this is 1788, this was all done before they had tools to do mechanical analysis, or mathematical analysis like we have now. So this is all done basically on intuition more than anything in terms of how this works.
Was that like the mechanical system like controlled by like a person, or was it based on the fact that like if they were going like on like a decline that it would speed up, so that like the system would speed up so it would close it to like slow it down?
So I imagine there was some probably like set screws or other things to adjust what it was, but it's all self-regulating. So the idea is that the speed is directly transduced to this rotating element, this centrifugal governor. And so regardless of you're going up a hill or down a hill, right, you want a certain height of the balls going out, right? So that changes then the throttle position. Yes?
How would you control the speed of a steam engine? Wouldn't that would just give you like a constant speed, right? This mechanism on its own.
So again, so this is set to give a constant speed.
Yeah.
That's the idea. Yeah.
Okay.
Yeah.
So maybe okay.
So
if you wanted to change your speed, you just wouldn't have power.
you'd have to change if you wanted to change the speed. I don't know. I've never worked on a 1788 steam engine, but you see elements here where you can have like screw adjustment.
Okay.
So if you wanted like, train engineer A says I want to go faster than train engineer B, they would adjust that mechanical element to change what the set point is. Okay, so other examples, air temperature control. This is basically the same whether if it's air conditioning or if it's the temperature of your oven or the heating in your house, right? These are really, really simple controllers. So simple, but actually fairly difficult to analyze because you have, as the question was asked before, what could you have logic baked into this? When you have logic, that's talking about discontinuous actions, which is more difficult to model. But the main idea behind, say, an air conditioning system is that you're continually monitoring the temperatures with some sort of thermometer. If the temperature gets too high, you turn the compressor in your air conditioner on. That cools the room. If it gets too low, then you turn the compressor off. Then the temperature of the room heats up. Right? So very, very simple controllers. It's looking at the output being the temperature of the room, the input, the basically compressor to your air conditioner, and then you're looking at essentially how far you are away from some sort of set point, which is this middle part with what's called hysteresis bounds on it. Okay, so we're not trying to keep the temperature exactly at T naught, we're just trying to keep it in some vicinity of T naught. If it gets too far away, then we do an action, right? Either turn on or off the compressor is the idea. All right, so this, okay. I'll skip the one of the phones. The examples are getting a little, this is what's called the hippie control system. So hippies, just like us, they have these sensors in their ears, which actually can sense the position of their head. And so then if they're on a slack line, they can't look at and understand what is the position of the body. Even though they may be tumbling on this here. And so just like us two, they do have brains, hippies. And so then they can change their angle of their arms, angle of their body, etc., based off this information to then try to stay upright on the sun. So again, the idea is that you have some sort of desired output, right, which is some sort of upright position. You can sense then how upright you are and then make actions via actuating your muscles to then try and stay upright on a slack line. Good. All right, so the idea of control from a more of a mathematical point of view, these are kind of like broad overview examples of control systems you may see in your everyday life. Is it fundamentally changes how a system behaves. No idea. So if we look at our standard control loop, all right, so we have our standard control loop here. And if you want to understand what C over R is, and we have G1, G2 in this system, we can go through the derivation of this really quickly. Here's the fundamental control loop here. If I want to describe C as a function of our air signal, then I would say that C, and I'll drop the S's for convenience. From here forward in this class, we'll be working almost purely in the frequency domain, or S variables, and so I'll be dropping the S variable quite often because it's going to get redundant. Everything pretty much, unless the exception will be when we're working in the time domain, actually. And so we'll indicate we're in the time domain by giving it as a function of t. Almost always we'll be working in the frequency domain. And so we would say that C is equal to G1, G2, E, and then we would say that E is equal to R minus C. So putting E in this expression here, I get C is equal to G1, G2, R minus C. I can move the C over to the left-hand side. So I get then, I can move the G1, G2 minus C over to, the negative G1, G2, C over to the left-hand side. That gives me C 1 plus G1, G2 is equal to G1, G2, R. And then if I want to know what is the transfer function, C over R, it's going to be G1, G2 over 1 plus G1, G2. Okay, so I'm doing this once. If this is something that you don't remember in terms of very well from 3260 and how to look at block diagrams, how to rearrange them to get condense them into a single block, I would encourage you to look back at your notes from 3260 or commit this to memory. So we will be using this transfer function, or you will be, I'm guessing somewhere on the order of 100 times between now and the end of the semester. Okay, so you will see this over and over and over again, right, in terms of making this expression for C over R. So I wouldn't say commit this to memory, it'll just probably happen, okay, over time. Right? But we're going to be looking at this all the time. So this is the general transfer function for the output with respect to the reference signal based off of the transfer function for your plant. So in general, the plant is given to you. Someone says, control engineer, control the systems, and your design often is to design G1, such that the whole system will respond in a favorable manner. Okay, so if we were to parameterize G1 and G2, we can say that G1 is composed of a numerator, B1, and a denominator, A1, right? So this is a transfer function that's going to have, say, a polynomial numerator, polynomial in the denominator. G2 is the plant, which also is a transfer function, which could be composed of a numerator and denominator. Okay? And so say you are given a plant, and the plant is naturally unstable, right? An inverted pendulum is a case of an unstable system, right? So that means that you're going to have poles in the right half plane of that system, which is obviously not desirable. What this allows us to do is actually change the transfer function for C over R such the poles are no longer in the right half plane. All right, so the way in which this happens, we can look at this from the perspective that we just, all right, now insert these expressions for G1 and G2 into our equation here. I'm going to get then, in the numerator, I'm going to get B1 over A1, B2 over A2. In the denominator, I'm going to get a slightly different expression. Right. And then if I want to simplify this, I can multiply top and bottom by A1, A2. And this gives me B1, B2, A1, A2, plus B1, B2. Okay, so if we had a system in which the poles of that system, or the plant, so the poles of that plant were in the right half plane, via the fact that we have addition here, all right, I can now change the poles of C over R such that they are in different locations. All right, so via the design of A1 and B1, I can start to move these poles around, and so that allows me to change so that if G2 behaved unfavorably, I can still make sure that C over R behaves in a favorable manner. So it's with certain limitations. We'll talk a little bit about limitations in this class. Not too much, but we'll talk about some of those limitations. Okay. All right. So we talked about the idea that we want to make sure, or we talked about the idea that if we have poles in the right half plane, that's going to result in an unstable system, or that's going to correspond to solutions C that explode in time. In general, our idea is that we're going to make sure that all our poles are in the left half plane. So if you remember one thing from this class, it should be that when we're designing control systems, we want all the poles to be in the left half plane. We want stable solutions. That's like a bare minimum to graduate this class, pass this class. Does anyone know an exception to this case, where you can have poles in the right half plane and still be stable? Any thoughts? Karsten?
There's like a physical limitation, like they can't physically go much past a certain area.
So mathematically, it's still unstable, even in that case. No, we'll talk about that. Don't ever do that. Yeah. Pole zero cancellations are, that'll be the next lecture, yeah. Any other thoughts? Okay, so the only exception, this is a trick question, is Chuck Norris. So, so Chuck Norris has poles in the right half plane, he's still stable. Everything else is unstable. All right, so this is a patch. This is not mine. I have a friend who does a lot of control systems on aircraft, and they look at, all right, what happens if you lose an engine? How do you still maintain stability? And this was the patches that they had for their flight jackets for their test. And they have Chuck is stable in the right half plane. So, and then usually with control systems, you try and predict and then validate. And so Chuck doesn't predict and validate; he just kills, predicts and kills. So I know. I thought this was funny. So, all right. So the idea here. This is going back to content from 3260 and then lecture 3, where we have this general map of pole locations and time domain solutions that if you have pole locations in the left half plane, you have these nice convergent solutions, and we'll talk a lot about pole locations and how this corresponds to responses. But we are never going to place poles in this right half plane, so never design poles to be here. And then in general, if we have poles that are really close to the imaginary axis or on the imaginary axis, the system will oscillate forever. There are a few examples of where this is desirable to actually have this happen. You can think of systems that you want to oscillate, like there are a lot of things in electronics that you want to have. You want to design oscillators. In general, this is very unfavorable. So oftentimes, designing poles to be on the imaginary axis, this is a bad idea often as well. Okay, so just kind of to give general idea of what we're talking about here with a controlled system, what this allows us to do. Because this allows us to start to move around the poles of the system, the C over R, what we're doing, we're changing the pole locations, we're changing the basic fundamental characteristics of the system, right? So by changing the pole system, what this allows us to do is a slow system fast. Okay, so if the system or the plant naturally has poles that are close to the origin, so therefore they correspond to really slowly decaying exponentials, we can move them such that it acts in a faster way. Now this does have limitations. We can't, say, make a semi-truck be as fast as a Maserati, right? That's not going to happen. There are limitations to this, but we can change behavior. We can make a fast system slow. We can make unstable systems stable. Okay, so this is important for a lot of different applications. As you get it into the end of project part 2, you're going to see that in the case of your pendulum system, in any angle greater than pi over 2, one of your poles is going to pop into the right half plane. Right, and that's going to be an unstable system, right? And so we are able, with control, to still control that pendulum angle, even though it's in the right half plane, because we can move, via control systems, move those poles into the left half plane. And then the last thing you can do, which is undesirable, make a stable system unstable. This is never the intention, but it can happen. So let's underline that exclamation point. We'll talk about how this could pretty easily happen with control systems in this class. But you can take a perfectly stable system, say for instance your car, right? If you were to let off the accelerator in your car, it's just going to eventually go speed, right? You expect your speed just also to take off, right? But if the engineers at GM or Ford design that control system incorrectly, you can actually have a system that be extremely dangerous to the passengers of the car. Right, so we'll talk about how you can show to make sure a system's stable, because you can definitely drive perfectly stable systems unstable once you wrap the feedback loop around. Right, so that's something you have to be mindful of as engineers who care for the safety of the people who use our products. All right, any general questions about that before we get into some mathematical descriptions of control systems? All right, so we're going to talk about general behaviors. This is just a start to all this with proportional control, and we're going to look at the most basic system that we can really start with, and that is a mass spring damper system that we are somehow forcing with some sort of motor system. Right? This is like your standard prototypical control system. And so the general idea here is we have some sort of mass spring damper. Now note that not all systems look like this, right? So you can have other mechanical systems that don't have a spring, right? This element could not be there, right? So everything that we're talking about in this example is going to be in reference to this system, which does have a spring in it. And we'll talk a lot about how different components affect the plant, but let's just start here, and then we'll work on that later. So we have a general mass spring damper system has position C. I'm using the variable C because that's what the book by Nice uses. And then we have the ability to force the system. And this force is given by a motor system And this is a very simple motor source system that has a current source. So oftentimes in this class thus far, we've looked at systems with voltage sources. That's the less expensive option to do it. A lot of control systems have current sources built into them. And so then we have that the force delivered by this motor is given by some sort of force constant, and then the current running through this motor. So here we're stripping out a lot of the complexities we talked about with motor systems, where you have a torque constant, back EMF, you have transmissions to, if we're looking at mass spring damper, to translate rotary motion into linear motion. We're just making this as simple as possible right now and saying that we have some sort of force which is proportional to the current put into this electrical system. Okay. And so then, if we want to try and understand the behavior of the system, we want to understand then this transfer function C over R. That's what we're trying to get to here. And so to build up into that, we're just going to quickly look at what the equations of motion are for the system. So we have our equations of motion, which look a lot like a lot of the other equations of motion we've been writing lately. Right, this is all in the time domain. We're going to almost immediately, with all these problems, jump into the frequency domain by taking the Laplace transform of this. And if we're looking at transfer functions, remember the definition of a transfer function is a Laplace transform with the assumption that all the initial conditions are equal to 0. Right? All right, so this is assuming then that the system's initially at rest. We click some sort of on button, or flip some sort of on button, right? And then we look at how does the system respond from there on. Right? All right, so if I then, this is our plan. I guess I should have mentioned that this is our plan. Yes? So if we had, okay, so you're saying that we do have some sort of initial condition to our system. It's just the Laplace transform. Yeah, no other name for it. It's not, you can't write a transfer function for that. So I guess I will say this, is that everything that we're going to learn from looking at the transfer function, we can apply to the cases where we have non-zero initial conditions. With respect to that, we expect the control system to drive the system to some sort of reference position. So if it has some sort of initial velocity to it, and our reference says do not have initial velocity, it's going to eventually drive it to some sort of no velocity. Right? So it's going to have some transient associated with it, that's for sure. Yeah. Since you're so interested, there are other constructs that handle initial conditions better than transfer functions. That's more in the graduate level classes. All right, so this is the Laplace transform of our plant. And so if we want to say, all right, what is the plant? Our plant is this transfer function, G2. And our output is our position, if we're trying to control position. Our input is the current into the system. And then the transfer function then for this would be Kf. Ms squared plus Bs plus K. All right, so in terms of defining what is our plant transfer function, this is it. All right, this is a description of our physical system that we're trying to control. I forget, I glossed over this in the problem statement. I probably should have went through this a little more carefully. But here we're trying to understand how a single proportional gain, Kp, affects our system. All right, so we're saying, all right, there are an infinite number of choices for the design of this controller. Let's start for our basic analysis with proportional control. And what proportional control means is that we have this feedback loop, we have our plant, and then we have this term, G1 is equal to Kp. So that means if we have an error signal, E, that means that U of S is simply equal to Kp E of S. And in the time domain, that means that U of T, or in this example, U is the input to our system, the input to our plant is I, right? That's the current in our system. IT is equal to Kp E of T. Okay, so in terms of what this means, if you ever to build this system, you would have some sort of microcontroller or a computer attached to your system, and you'd have somewhere in your code a line that says that compute the error signal. This means subtracting the desired position from the actual measured position. That's your error. Multiply that by your proportion, Kp. So, for instance, this could be 1 or it could be 10 or whatever you design it to be. And then in this transition from the virtual to the physical world via basically digital analog converters, then the current to your system would then be Kp times E, right? So it's basically says send out then this value for your input to the plant, would be the idea. All right. So if we look at then what is the transfer function for our controller, it is again I is output over input. So G1 is I over E, which is simply Kp. Right. So this is the simplest controller we can possibly design. All right, so then getting to what C over R is. C over R, given the template that we have in terms of what is this transfer function, is equal to G1 times G2. So here's G1, it's really simple, it's just Kp. G2 is more complex, it is Kf over ms squared plus bs plus k over 1 plus G1, G2. All right, and then we want to simplify this. So I'm going to multiply top and bottom by this denominator, ms squared plus bs plus k. To give me the more simple relationship, Kp, Kf over ms squared plus bs plus then Kp, or k plus Kp, Kf. And if I wanted to, in the last minute here, I can divide everything by m. So oftentimes we're going to get this in standard form. Dividing everything by m, that would give me Kp, Kf, divided by m, s squared plus b over m plus k plus kpf over m. Yes?
How did you know that G1 was I over E?
So that was basically given the construction of the system. So our input to our system is current, right? That's what drives the system. And so the controller is always going to be relating via this loop. In general, the generic form for the input is U, but in this case, because the input to the plant is I, or current, we call it I. So it's basically G1 is this relationship, this transfer function. Did I get your question? Yeah, and then it was in the problem statement said that we're going to look at just proportional control, which has this design. Okay, So in the last minute, just to kind of comment on why this is important. All right, so say we were to purchase this motor system, right, which is a mass spring damper. Everything in that system cost, who knows how much it cost, right? But maybe it cost you a few $100s, right, by the time you buy the motors and the mass and everything. And to change any of those elements would be fairly expensive, not incredibly expensive, but depends what it is, I guess. But each of those requires basically disassembling the system. This KP, this just lives in your computer, right? Here, and it shows up here, right? And so this, to change how the system behaves, if we look at what the S to 0 term, this corresponds to natural frequency, right? So we can actually change the natural frequency of our system just by changing a line in code, recompiling, and running again, right? So it's a very quick, easy way to change how a system fundamentally behaves by just tuning something that's really inexpensive to change. Yes? So that is, this problem is just specify that we're going to look at proportional control. Okay. So if the problem says something different, we're going to look through a lot of different control designs, one of them being proportional integral derivative control, which is, that's like the one that's used ubiquitously across the industry, and then we're looking at other ones called lead lag controllers. It would be based on design. So this is just the simplest thing we can do to start off the discussion. Okay, see you on Friday then.